Today we want to take a look at sine and cosine more as functions, like other functions we've talked about. And so that means graphing them, and graphing them on a two-axis kind of setup. So it's a little bit strange because when we've been talking about trig, in terms of taking trig of angles that have rotated around a circle, we already have some, yes, I make up words, graphiness going on, okay? Because we say that within that circle we have our horizontal axis, we have our vertical axis, and it's like x and y, and we've divided the circle into quadrants, and so there's kind of this graph kind of thing going on already. But what we now need to do is actually just look at one trig function at a time and graph it in a way that is more normal, where we have, for example, the sine function in relationship to what the angle is, and we just look at sine. Okay, we're not in a situation where we've actually got cosine and tangent and things like that going on as well. So the first thing I just want to show you is kind of what we're looking at when we do this graph. Our x-axis now represents the angle measure in the rotation around. And if we're trying to look at, this is for sine of x, if we're trying to look at the sine, we know now that on a unit circle, the sine of x is simply the y value for the point on the terminal side as it rotates around the circle. And so this graphic shows you that if I increase the angle measure and rotate it around starting at 0, 0, that as I do that, we can take what that y value is, or what that height is of the point above that x-axis, and plot it. So this is actually pi over 12. There's pi over 6, pi over 4, pi over 3, 5 pi over 12, pi over 2. And you can see how as I rotate around, that y value on my point gets bigger and bigger and bigger until I get to this angle, pi over 2. Because this is my maximum distance away from the x-axis that I can get. And as I continue to rotate around, we can see now that the y values start getting smaller and smaller until I'm back over here at pi on the x-axis. And if I continue from there, my distance gets bigger again, but now I'm underneath the x-axis in my unit circle, and so I end up with negative values on my graph. Right?
So that works.
And that's going to go until 3 pi over 2, where I get the farthest away from the x-axis but in the negative direction. And then my distance shortens again until I'm back up here to 2 pi. So this graph that we call the sine graph, the sine curve, comes from just looking at those y values from the point as it rotates around the circle. Okay? And then whatever this pattern is that we get from one rotation around, that pattern just keeps repeating itself. So if I keep going out further and further to the right, we're just going to keep repeating that wave pattern. If I go out to the left, that means we're actually going clockwise around, and so I'm getting negative angles, and therefore this could keep going out this way as well. And we just get this wave function. And because of the repetitiveness of it, this is what's called a periodic function. You've ever heard of trigonometry referred to as the periodic functions? It's because of how this pattern for the graph just keeps repeating itself over and over and over again. Okay? The pattern for sine is significant. There's actually some books that refer to the 5-point pattern that sine and cosine have. So with sine, the 5-point pattern is to start here on our y-axis. Well, that starts at a 0. And then from 0, we go up to a max, back down to a 0, down to a min, and back up to a 0. So the 5-point pattern for sine is 0, max, 0, min, 0. Okay, and that's going to be significant for us in a couple of minutes to help us with graphing. Okay, cosine is similar, but now what are we going to be looking at? Distances of what? The x value. So if we do the same kind of thing now, starting at an angle of 0, but now measuring our x values, at 0 I actually start with my longest value. Right? Because going out to the circle there on my x-axis is going to be my +1. And as I start rotating around, my distance out horizontally before I go up to that point starts shrinking. So we're actually starting at the maximum value and then shrinking down until we get to pi/2. Because now if I'm at the y-axis on my unit circle, my actual x value is 0. Right? And then when I continue to rotate, because I'm now over on the left side of the y-axis on my unit circle, that means I'm getting negative cosines in my graph. And it also means that my distance is getting bigger and bigger and bigger. Until I get out here to pi, which is my furthest distance, but it's my furthest distance to the left. So that puts me out at a -1. And then we keep rotating, and I'm still negative now, because in the third quadrant, cosine is still negative, but now my lengths start shortening up again until I get here to 3pi/2. And then fourth quadrant, we're back to being on the right side, so we're back to positive cosine answers, and we're back up to where we started.
It's the same 5-point pattern for this.
So what's the 5-point pattern for this one?
Max 0, 0, max.
Right. So we're starting at a max value with cosine, whereas we started with a 0 with sine. Now, there are a lot of similarities, though. Basically, the cosine function is simply the sine function shifted 90 degrees, which is actually where cosine comes from. It's short for complementary sine. Right? Complements are 90 degrees. So the cosine is the complementary sine. It's the sine shifted 90 degrees, or pi/2. So in terms of the wave you see, it's the same kind of wave. There's going to be a lot of similarities that we're going to see here in just a minute. But one of the significant differences is that actual 5-point pattern. Because with cosine, we start at a max and go max, 0, min, 0, max. With sine, we start at a 0 and go 0, max, 0, min, 0. Okay? Questions on that? Where those are coming from? Yeah?
Just out of curiosity, will we ever have like a vocab on the test?
Possibly in the objective ones. There might be like matching vocab or multiple choice vocab. Or it could be vocab related. All right, so looking at sine and cosine as functions and looking at the graphs of them, I thought it might be a good time to go back to our analysis book and actually analyze sine and cosine, because we haven't gotten that far yet. We did all the other functions up to there, but we hadn't gotten to sine and cosine. So if you have your function book, go ahead and record this in there. If you don't have it with you today, take some notes on it and then get it transferred over to your function book when you have a chance.
So this is sine. Right?
So we're going to start with sine. Yep. All right, so our x value now, sorry, our x-axis now is still x, but we need to realize that what that represents are angle measurements. Okay, usually in radians. They don't have to be, sometimes we graph them in degrees, but usually we graph them in radians just because it's a little simpler and a little cleaner. Our y-axis is now going to represent the kinds of answers we get when we take the sine. Okay, so when you set this up, how many radians does it take to complete one full pattern?
2 pi.
2 pi, right? Once around the circle completes one full pattern, and that's going to be 2 pi. So when you set these up, the way I recommend you set them up is to start out with your x-axis and set up 4 tick marks. Okay? And I'm going to go every 2 boxes here for these tick marks. So that's a pretty good spacing. And on your 4th tick mark, you're going to label that 2 pi. Because that's how much space it takes to complete one pattern. Right? One revolution around. And then we can label the rest of the tick marks by kind of having things up. So half of 2 pi is going to be pi, so that's this tick mark. Half of that's going to be pi over 2, so that's going to be that tick mark. And then what's this one going to be? 3 pi over 2. Okay? That space that it takes, and we're going to come back and talk about this a little bit more in a second, but that space, that number of radians it takes to get through one full pattern is called a period. And a lot of times when you're asked to graph these, you are asked to graph 2 full periods. So, from 0 to positive 2 pi will give me 1. I'm going to set up the same kind of scale on this side. And that way I've got things set up that I can get 2 full periods in there. Okay? I also need a scale for my y-axis. What are the maximum and minimum values that sine can have? And remember, we're just talking parent function right now, just nothing fancy, right? So what is it? 1 and -1. So, just to give myself a little bit of space here, I'm going to go 3 boxes to get to 1 and down to -1. Okay, so if we follow that pattern again, for sine the pattern was what? 0 max, 0 min, 0. So the 5 points of that pattern happen now on the tick marks. Right? I start here on my y-axis at 0, and then the next tick mark puts me at max, next tick mark puts me at 0, next tick mark puts me at min, and the next tick mark puts me back at 0. So if we set up these 4 tick marks, they're going to fit that 5-point pattern. And then I continue the pattern to the left, but I have to realize that continuing the pattern means I have to actually go down first, 0, back up, 0. And now when you go to draw this, please draw it as a wave, not as a mountain range. Okay? These are curved off at these max and min points. They are not pointy. Okay? So make sure you're drawing it kind of curved off, something like this. And there's our sine of x. Okay? Now, to analyze it, what's our domain going to be? All real numbers, negative infinity to positive infinity. There's no restriction on what angle measure I can use to take the sine. So domain's going to be all real numbers. Range, parentheses or square brackets?
Square bracket.
Square brackets, because we're going to include both the positive and the negative 1. We have actual points there with actual y values, so we want to include those numbers. All right, here comes the fun stuff. Zeros of the function. How many do we have? Infinitely many. Because if this keeps going off to the right, up and down and up and down, every time it bounces back and forth between 1 and negative 1, it's going to cross the dang x-axis. And every time it does it off to the left, it's going to keep crossing the dang x-axis. And every time it crosses, we got a 0. So how am I supposed to list what the zeros over the function are if there are infinitely many of them? That's where we're going to start. So what would be the zeros between, actually we're just going to start with 1 rotation. We're not even going to go all the way to negative 2 pi. We're just going to go from 0 to 2 pi. One pattern, one rotation around the circle. Where are my zeros?
0 and pi.
0, pi, and 2 pi technically is being back to 0, right? So we're going to list 0 and pi. Now, how often does that 0, the one that happens at the beginning of the pattern, repeat itself? Space-wise. How many radians does it take before that point repeats itself?
2 pi.
2 pi. Because the period is 2 pi, right? That's how much space it takes to repeat itself. So that particular point is going to repeat itself every 2 pi. So the accepted way of showing that is to say I'm going to add a 2 pi n.
Where n is the period.
Close. N is going to be an integer. Okay? Has to be an integer. Can't be a fraction. It's got to be an integer because it's got to represent how many full cycles we're going through. So if n is a positive integer, then that means we continue to rotate counterclockwise and we would continue to go out this way. If n happens to be a negative integer, then that means we started rotating clockwise and n would keep going out this way. So if n was a 3, it means taking this and repeating it 3 times to be talking about what's happening there. If n was a negative 2, it would mean taking this and repeating it again to talk about what's happening there. Okay? So any x values where things happen, the way to show the repetitiveness and actually represent all of them is to add this 2 pi n expression. And when you're adding it to 0, if you want to drop the 0 and just say it's 2 pi n, that's fine. Or you can leave the 0 there for emphasis, either way. Okay? So the same thing happens with increasing, decreasing, and constant, because those are supposed to be intervals of x values. Hang on just a second, I'll come back to you. Right? So if they're on intervals of x values, then that means every 2 pi of x values, this pattern is going to repeat itself again. So when I say that I'm going to increase here, because that's what my graph starts out by doing, we're going to go up. And we're going to go up from x values of 0 to pi over 2. But instead of just writing 0 to pi over 2, we're going to write 0 plus 2 pi n, and pi over 2 plus 2 pi n, to represent every time we get this first little piece that's increasing. So every time it repeats itself over and over again. Okay? Same thing for the next piece. The next piece is decreasing. It's going to go from pi over 2 until 3 pi over 2. So that's the interval on the 1 period. We then represent every period by adding 2 pi n to those two values.
Mrs. Gordon, I can't read. What did you write after increasing 0 plus what?
0 plus 2 pi n, comma, positive over 2 plus 2 pi n. So the first increasing piece is from 0 to pi over 2 in this 1 period, right? But then we added the plus 2 pi n to each of those to show, so there's this piece, and then there's this piece, and then there's this piece, and then there's this piece. It keeps repeating itself. Okay? So same with decreasing. From pi over 2 to 3 pi over 2 is now the down part of my graph. But again, adding the 2 pi over 2 pi n to each of those means there's this piece, and then there'd be that piece again, and that piece again, and there's that piece going this way. Okay? And then finally, let me finish this up, and then I'll take questions. The last little bit of increasing piece right here is going to go from 3 pi over 2 plus 2 pi n up to 2 pi plus 2 pi n, and that takes care of all of it. Everything's been represented now. Okay? Jonathan, question?
For the zeros of the function, couldn't you also just write 0 plus pi n? Because then when it's 0, it'd be 0.
Yeah. You could. I kind of like to write it this way because it emphasizes the fact that our period is 2 pi and therefore it's every 2 pi that things start repeating themselves. But you'd be saying the same thing if you did it the other way. Yeah.
Oh yeah, so you would need the second one, right?
Yeah, so if you did 0 plus pi n here, then you don't need this one because it already takes care of it. So you could do that.
Shouldn't 2 pi be in the row? That's part of the period. So 2 pi plus 2 pi n. Or does like?
You mean here?
No, the zeros of the function.
Oh, no, because technically once I get to 2 pi, I've gone all the way around the circle and I'm back at what was 0.
Oh.
So that's where like the next piece starts repeating itself, so we don't really include it in the first period because it's the beginning of the next period.
So it's a new one starts at the same time.
Yep.
Could you write the increasing was like negative 2 pi, or negative pi over 2 to pi over 2, or not really?
Yeah, you probably could. All right, max and min points. How many maxes do we have? Another one of those infinitely many. How many mins do we have? Another infinitely many. So same kind of thing's going to happen here. However, the way we write it is going to be just a little bit different because now we're talking about ordered pairs. So where is the max point in this 1 period? What's the ordered pair?
Pi over 2, 1.
Pi over 2, 1. Okay? So then to represent every max point, again, we just add that 2 pi n. But we only add it to x. Because every time I get a max point, the y value is always 1. It doesn't change. So it's only the x value that's going to get the plus 2 pi n adjustments in this ordered pair. Because the y value doesn't change each time. Okay? And then where's our minimum value in the first period?
3 over 2 pi.
So what?
3 pi over 2.
3 pi over 2. 3 over 2 pi is different. So 3 pi over 2, that's the one that's going to get the adjustment to show everything. But then what's my y value going to be?
Negative 1.
Negative 1, and it just is negative 1 every time. So y doesn't change. And this one we really can't just say, oh, well, can't I just say pi over 2 and then plus pi n every time? No, because the next pi is a min, not a max. So this one we really do have to write this way. All right, last couple. Even or odd?
May have forgotten what.
There's even.
Even, oh, it has to do with like where it's mirrored.
It's related to symmetry, but remember it's different than symmetry.
Neither, I think.
It's not
I could be wrong.
You gotta flip it.
We don't think it.
So if you flip it, does it look exactly the same? And I don't mean flip it, I mean turn it upside down.
Mm,
No.
Yes. Yes, it does.
No.
Yeah.
but it's
Have you drawn it on your paper?
Yeah,
Turn
if
it
you
upside
do,
down.
If you do that, it's the same.
Well, do you
Oh, it's the same
Maybe
shape,
like
it's in a different spot.
like twist it
Oh, it's-
upside down, or
it's
is it
the same
like
spot.
In a different
90
spot.
It's shifted 90
It's
It's the same.
Yeah, 50 degrees.
No, dude. Hey, look. And then.
Starts at 0, 0.
I'm not gonna
You
explain
go
this, man.
pi over 2 to the right, you're
Still
going to
there.
a
I'm
max.
bad
You go
drawing.
pi over 2 to the left, you're going to a min. Yeah, it's the same. So that means it has symmetry with the origin, and that makes it an odd function. Okay?
Right.
Any asymptotes?
None.
Nope. Even though we are limited as to how high or how low we go, there's no asymptote to it because we're not getting closer and closer to that value. Okay, it's just a limit. So none there. And then end behavior.
None.
There isn't any because our end behavior doesn't do just one thing. It's not just going higher and higher, it's not just going lower and lower, it's not just going to one number. It just keeps bouncing back and forth between the numbers. So really for end behavior, we just say it's not applicable. There isn't really any. Okay? Any questions? All right, so for your homework, part of your homework tonight, oops, do that first. I want you to
That's speed.
analyze cosine. Okay, you're gonna draw it, you're gonna analyze it, it's part of your homework tonight. Now, really quick, to show you what you actually need to do in the homework. I hope for some of you this is pretty familiar, so we can do just a really quick review. When we do translations with sine and cosine, it's still about a, b, h, and k, just like it was for every other function we've talked about so far. And in general, the effects of a, b, h, and k are the same. The weird part, though, is that with sine and cosine, we actually have certain names for some of those changes that get made. So for example, amplitude. Amplitude will come from the absolute value of your A value, which normally we just say creates vertical stretch or shrink. But if you think about the shape now, a vertical stretch means that the distance from my axis up to this max point, if I start stretching it, that distance increases. And that distance is what we call amplitude. So the actual definition is distance from the, you ready for this? I love this word. Sinusoidal. It's so much fun to say. Sinusoidal axis to a max or min point. Okay? So it doesn't matter if you're going to max or going to min. What matters is what that distance is.
Maybe it would
And the sinusoidal axis is simply the axis that runs horizontally right down the middle of your graph.
Oh, we use
So
that.
in the parent function, it's the x-axis, right? But if things start moving around, that axis is going to move as well. So your sinusoidal axis is the horizontal, whoops, okay, let's try that again. Horizontal line through middle of graph. So what's going to affect where your sinusoidal axis is? A, B, H, or K?
K.
K. Because if K moves things up or down, that horizontal line is also going to move up or down. So K is going to affect that. The period, we've already talked a little bit about it being the space that it takes to complete one curve, one rotation, one pattern. That is based on our B value. Because B, remember, is horizontal stretch or shrink. Right? So if I do a horizontal shrink, what was 2 pi is now going to shorten up to something else. Or what was 2 pi, if I stretch it, now takes longer. Okay? So to find the period, we take 2 pi and simply divide it by that absolute value B. That'll tell you what the period's supposed to be. All right, so really quick before the bell rings. Let's say this is our question. First thing I still recommend is just like we did with every other function, identify what A, B, H, and K are first, so you know what kind of effect they are. Really quick. A is what?
-1.
B.
Pi.
H.
None.
K.
2.
2. K tells me where my new sinusoidal axis is. Boom. What's my period going to be if B is pi?
Pi. No, 2.
2. Set up your axes the same way. Hang on. I can get through this much quicker if you just sit and listen for just a sec. Still set up your tick marks the same way. What's different is how we label them. Right? Now the last tick mark is 2 because that's the period. Halfway is 1, this is 1/2, this is 3/2, and so on. Tick marks this way, same way, we're going to label them. 1, that goes there, that goes there, that goes there. Okay? -1 means that from this new axis, my cosine is going to go down 1, whoops, that's just a 1, or up 1. But it's from the sinusoidal axis, not from the x-axis anymore. And when we do our pattern, the zeros are zeros on the sinusoidal axis. So this -1 means that I have a 1 for an amplitude, and the negative means I flipped. So instead of the normal cosine of max 0, min 0, max, I have to start at a min. And then 0, max, 0, min, and then I've got what I need.
Cool.
Okay? So if you identify A, B, H, and K, everything else falls into place
You know
from that.
what
And you'll get a chance to practice it.
you didn't label, right? You just left for
Assignments on Canvas, do that plus your cosine analysis. If you have questions, be ready to ask on Wednesday. We'll see you then.
Oh, is it? Yeah.